Welcome. Welcome to the Plasma Physics course of TPFL. In the last module, we have introduced the Boltzmann equation. When we have introduced this equation, we have separated the long-range forces, what we called associated to collective effect, from the short-range forces, the ones that are associated with collisions. Now, let me first say that in a plasma, according to the definition of plasmas, long-range collective effects have to dominate over collisions. However, despite this fact, collision may still play an important role, and therefore it's worth looking at those and studying what is the effect of collisions in a plasma. What we will do in the present module will be to give a basic introduction to collisions. Now, the particles present in a plasma can collide both with neutrals and with other charged particles. The most interesting collisions are the one against other charged particles, Coulomb collision, and this is what we will focus our attention on. We will therefore introduce the basic concept, the one of collision frequency, cross-section, that are useful to analyze the Coulomb collision in a plasma. The first thing that we want to do is to give a simple estimate of the Coulomb collision frequency. It's something that we have already mentioned while giving the rigorous definition of a plasma. So let's do it now a bit more rigorously. Let's suppose that we have an electron that moves and goes across a heavy ion with a charge Z times E. Because of the Coulomb interaction that exists between these two charged particles, then the trajectory of the electrons, which is initially moving in this direction, will be deviated. We will call VE the initial velocity of the electrons, and we will denote with B the distance that I have pointed out here. Basically, the impact parameter, the shortest distance at which the electrons and the ions will be if the electrons trajectory was not modified. Let's try to estimate when the deviation due to this Coulomb force starts to be important. Well, what we have to do is to evaluate the ratio between the Coulomb interaction energy and the kinetic energy. That is, for the kinetic energy, MEV E squared, and for the Coulomb interaction energy, this will be given by the charge, the product of the two charges of the two particles divided by 4 pi epsilon 0 b. And the deviation of the trajectory will start to be important when this ratio is about 1. This means that the impact parameters at which Coulomb interaction become important can be estimated and will be equal to Z E squared divided by 4 pi epsilon 0 MEVE squared. And this quantity, for reasons that we will explain later, is actually a name and is called B pi over 2. At this point, we can evaluate the Coulomb cross-section, which is the area effectively seen by the electron moving towards this ion, and can be estimated as pi b squared over b pi over 2 squared. We will call this cross-section, as it's associated to the b pi over 2 parameter, as sigma pi over 2, and therefore, using the expression that we have just given, will be given by pi here, z squared e to the power 4 pi epsilon 0 square me squared ve to the power 4. From this we can derive a collision frequency that is given by the product of the target density, the incoming electron velocity, and the cross-section, which by plugging all the numbers we have put here will be given by the ratio of Ni, the target density, the density of the ion, z square e to the power 4, and again 4 pi epsilon 0 square me squared ve to the power 3. So we actually have some questions that have to be associated with this simple estimate. The first one, is this a correct estimate? It's so simple if you want. In particular, what we have supposed here is that these are collisions where there is a large deflection of the trajectory of the electron. So, in general, do small angle deflection matter in a plasma, or shall we just count for this large angle deflection that we have described here? And second question. Here we have looked at the interaction of the electron with one single particle. Instead, as we know, there are many charged particles in a plasma. So how can we take into account properly the interaction with many particles? These are two questions that we are going to address with a more rigorous estimate of the collision frequency. So what we are going to do is now a more detailed evaluation of how the trajectory of an electron impacting towards an ion is modified because of the Coulomb interaction, and then we will take into account that the electrons interacts at the same time with all the other particles present in the system. So let's go back to our electrons impacting the ion. We will denote with theta the angle between the incoming velocity and the velocity after the collisions. More precisely, we will denote with theta this angle. Now, for two particles, such as the electron and the ion that we are considering, that are interacting through Coulomb force, one can show from the conservation of energy and angular momentum. We won't do all the steps, but this is a well-known result from classical mechanics. In the limit of me over mi much smaller than 1, well, from the conservation of energy and angular momentum, then one can show that the tangent of theta over 2 is equal to the ratio of the product of the two charges divided by 4 pi epsilon 0 me ve squared b. Now, the interesting thing is that this quantity z is e squared 4 pi epsilon 0 me ve squared is exactly what we have defined before as b pi over 2. So this tangent can be written as b of pi over 2 over b. And now the meaning of b of pi over 2 becomes clear. In fact, when b is equal to b pi over 2, then it's found that the tangent of theta over 2 is equal to 1. Therefore, that theta is equal to pi over 2. So b pi over 2 corresponds to the impact parameter at which the electron is deflected by 90 degrees. Now, taking this into account, the deflection due to each collision, we notice that in a plasma there are interactions with many particles. So what we want to address is what is the cumulative effect of these collisions. So more precisely what we have is, for example, an electron which is going towards a plasma. And what we want to know, to learn about, is how much this velocity will be deflected because of the interaction of these electrons with all the ions present in the plasma. In general, we will have that because of symmetry of this one-to-one collision, we will have that the deviation of the perpendicular electron velocity will be equal to 0. However, the spreading of the perpendicular electron velocity will not be equal to 0. Here with perpendicular and parallel, I will mean perpendicular and parallel to the initial velocity of the electron. Now, if we want to evaluate what is the spreading of the perpendicular velocity as a function of time, well, this derivative will be due to the interaction of the electrons with the particles that are all located at different impact parameters. And more precisely, what we will count are the particles that are in the differential cross-section that goes from B to B plus dB. And the number of these collisions will be equal to the target density times VE, the initial velocity, times the differential cross-section, that is this area among the two orange lines, is given by 2 pi b dB. And then each collision will give a certain delta V perp E squared, and then we will have to integrate over all possible impact parameters. Now, to make some progress, let me point out that this quantity can be expressed by knowing what is the deviation due to the Coulomb force. And in fact, delta V perp E is equal to VE sinus theta all squared. And now we can use one of the property of the sine function, that is sine of theta is equal to 2 sine theta over 2 cos theta over 2. And then dividing multiplying by cos squared theta over 2, we have that this is equal to 4 VE squared tangent of theta over 2 multiplied by cosine to the power 4. And this again, using the trigonometric identities, can be written in terms of tan of theta over 2. The nice thing of this expression is that the tangent of theta over 2 can be expressed in terms of b. And therefore these integrals becomes the integral the integral of this function that depends, as we have seen here, only from tangent of theta over 2 that we have expressed in terms of b pi over 2 over b. Now, what are the limits of integration of this function? Well, there are no issues for b that goes to 0, unless quantum effects will become important, but we have excluded to take into account those in our system. So the integral will go from 0 to, well, if you look here, for b that goes to infinity, what you actually have is an integral that will diverge. Why is that? Well, it's because we have assumed that the Coulomb interaction will be valid for at all distances, but as we know in a plasma, the Coulomb potential is screened at a distance that is comparable to the Debye length, and therefore there are no one-to-one particles at impact parameters that are greater than the Debye length. More precise calculation would have required to evaluate this expression by taking into account a screen Coulomb force, which we did not do. So we can replace this by basically limiting our integral to the Debye length of our plasma. And this integral can actually be solved analytically, and in the limit of the Debye length much larger than b pi over 2 is found to be equal to these quantities, which depends on the ion density, electron velocity, the b pi over 2 parameters, and the logarithm of the Debye length divided by the pi over 2 impact parameter. Well, this is a key result that allows us to make 3 observations. The first one is related to the evaluation of what is the change in the parallel velocity of the electron beam due to these collisions, to this ensemble of collisions. This can be done by noticing that the electrons do not lose much energy. So we can actually make 3 observations. The first one leads to the estimate of what is the change of the parallel electron velocity because of the multiple interaction with the ion present in a plasma. Why is that? Well, this is because the electrons impacting of these such heavy particles can be assimilated with the collision between for example, a ball against a wall. When you throw a ball against a wall, the ball changes considerably its velocity, but if the collision is elastic, then the ball is reflected with the modulus of the velocity that is similar to the previous one, to the incoming one, before the collision. Therefore, we have that because of conservation of energy, of electron energy, that the kinetic energy after the collision that is given by the sum of the parallel energy, which has been deviated by delta V parallel E, and the perpendicular energy is equal to the initial kinetic energy. From which, by developing t squared and eliminating v squared and v squared, we get that VE delta V parallel E plus 1/2 delta V perp E squared is equal to 0. In developing this expression, we have neglected delta V parallel square. This is valid for collisions leading to small deviation. As we will see in a few moments, it's a reasonable assumption for most of the collisions that occur in a plasma. From which, by inserting into this expression we obtain that time derivative of delta V parallel is equal to minus 4 pi ion density, electron velocity, B pi over 2 squared, and this logarithm. As a matter of fact, the logarithm of lambda d divided by b pi over 2 is coming back, and it has a name. We give it a name in plasma physics. We introduce the so-called Coulomb logarithm that we will denote as the logarithm of lambda, capital lambda, and is equal to the logarithm of the Debye length divided by b pi over 2. And well, lambda Debye can change a lot, b pi over 2 can change a lot. However, the ratio, and mostly the logarithm of the ratio, is fairly constant and throughout all the plasma that we have in the universe. In fact, in most plasma, the logarithm is between 15 and 25. The third observation is related to what we have just derived. Now, the variation of the parallel energy can be expressed in terms of frequency. That is the collision frequency of the electrons against the ions times the incoming velocity, where this collision frequency of the electrons against the ions is given by the expression that we can derive from here. And I realized that I forgot a squared here. Now, as the collision frequency is associated with a cross-section through the formula that follows, we have that the collision frequency, effective collision frequency for the incoming electrons impacting against the ions is equal to 4 pi b squared pi over 2 Coulomb logarithm. And now it's interesting to compare this cross-section with the one that we had evaluated just before, that was the cross-section relative to short impact parameters, pi b squared pi over 2. And this ratio will be equal to pi b pi over 2 squared divided by what we have just found here. And this is an easy ratio to evaluate because it will be given by 1 over 4 Coulomb logarithm. Coulomb logarithm is of the order of 20 times 4. This will be of the order of 10 to the minus 2. It's much, much smaller than 1. Conclusion? Conclusion is that small angle deflection, small angle collision play a dominant role with respect to the large deflection in a plasma, as this ratio is much smaller than 1. And this is consistent with what we have done earlier when we have neglected delta V parallel squared. To conclude the present module, let me say that what we have done was to introduce the main basic properties of Coulomb collisions in a plasma. We've started from simple order of magnitude estimate, and then we went more precise to study what are the cross-section and frequency of Coulomb collision in a plasma. We are now ready, and this is what we will do in the next module, to look at what are the consequences of collisions in a plasma.